Welcome to gravity video number 2. This is on acceleration of gravity. Now we know that on Earth, if I have a person that's just standing here, they will have a gravitational force pulling down, Fg, which is equal to their mass times what we call little g, the acceleration of gravity. Now if we imagine though that in our gravitational force equation, Fg equals g m1 m2 over r squared, if we imagine that m1 is our person and that m2 is whatever's causing that force, namely the Earth, then we can see that in fact this force here is the same as this force here, and we can set them equal, right? Because Fg equals Fg. So we have two ways of expressing what Fg is. We have Fg equals mg and Fg equals g m1 m2 over r squared. And so we can set them equal and say m times g is equal to g m1 m2 over r squared. Now m1, remember we said was this mass right here, and so this mass and this mass then are the same, and thus cancel out. And so here's what we have. Here's the result. We have g right here, big G, gravitational constant, m2 and r, and we have that g is equal to big G, m2, divided by r squared. But what is m2 equal? Well, m2, this we said was the Earth. And so in general, on Earth, we can see that g is equal to big G times the mass of the Earth divided by the distance that we are to the center of the Earth squared. And in fact, if I change this to just mass of the planet, then this would be a general form, a general equation for the acceleration of gravity at any point or anywhere in the universe for standing on the surface of a planet. Now what do we know this to be? We know that this equation on the surface of the Earth should yield g is equal to about 9.8 meters per second squared. And so if we take a look back at this table here, we've got Earth's radius and Earth's mass, I guess I did mass first and then radius, as those right there. So take a minute right now and calculate, based on this equation right here, what the acceleration of gravity at the surface of the Earth is going to be. Take a second and pause and come right back. Welcome back. When you did this, you should have plugged in 6.67 times 10 to the negative 11th as our big G. The mass of the Earth is 5.97 times 10 to the 24th kilograms, and we are dividing by the distance that we are to the center of the Earth, which is the radius of the Earth, which is 6378000, and we are squaring that. And when you do that, you get that g is equal to 9.788 meters per second squared. And if we take a look at that in comparison to our acceleration of gravity that we know it to be, 9.8, that is pretty darn close. Reasons for the differences could be this is an average radial distance. This is the average distance it is to the center of the Earth. This is an approximate mass, right? It only goes to 3 sig figs. So that changes as we go on here. Now, if we take a look at this equation as well, g equals big G, mass of the planet divided by r squared, we can see that as we get farther away, so as we get farther away from the center of the Earth, our gravity decreases. And that makes sense, right? We've talked about that before, that at the top of Mount Everest we have a lower acceleration of gravity than we do at the typical planetary distance, right? Or the radius of the Earth. And I want you to think about this. What happens as we go to the center of the Earth? and we'll talk about that next class. So that means because we know our general equation of acceleration of gravity, we can now figure out the acceleration of gravity on the moon and on Mars. So go ahead and, based on this chart right here, come up with the acceleration of gravity g moon on the moon and acceleration of gravity g Mars on Mars. I'll wait right here. Welcome back. As you went through this, you should have gotten that the gravity on the moon is approximately 1.6 meters per second squared, and the gravity on the surface of Mars is approximately 3.71 meters per second squared. Now let's take a look at how we got those. So remember, our equation for gravitational pull from a planet is given, or gravitational acceleration from a planet is given as our gravitational constant times the mass of the planet divided by the radius of the planet squared. So as we plug this in, 6.67 times 10 to the negative 11th times the mass of our planet, in this case it's the mass of the moon, 7.35 times 10 to the 22nd, and we are dividing it by the radius of the planet, 1.738 times 10 to the 6th squared. And as you do that, you get 1.6 meters per second squared. Similarly on Mars, g mass of Mars divided by the radius of Mars squared. And so we have 6.67 times 10 to the negative 11th times the mass of Mars, 6.42 times 10 to the 23rd. And we're dividing by the radius of Mars squared, 3.39 times 10 to the 6th squared. And as you go through that, you get 3.71 meters per second squared. And so this leads us to our final question of the day, or of the video at least, which is, if we had a planet, call it planet X, which has twice the mass of Earth, but is twice as big, so that is 2 times the radius, what would be the acceleration of gravity on the surface of that planet? And the key is to not use the mass of Earth or the radius of the Earth. If you can figure that out, you are a step ahead. See you next class.